I'll start the recording here. So in chapter 6, we study solutions to differential equations using power series. So like a solution like e to the x or e to the negative 2x, okay? Or a linear combination, c1 times e to the x plus c2 times e to the negative 2x, right? You've seen solutions like that. Well, an e to the x power or e to the negative 2x power can be written as a power series. And it is helpful sometimes to express solutions to differential equations as in terms of power series. You've been expressing solutions to differential equations in terms of linear combinations of functions. But those functions can be written and expressed as power series. And this is something in Calculus 2 that you learned, that you can express a function as a power series, particularly if the function is differentiable and continuous and that sort of thing. But of course, when you take a function and represent it as a power series, you learn in Calculus 2 that there is an interval of convergence. So for some functions, like if you have a function like e to the x power, okay, well that function e to the x power can be represented, and maybe let me just use my little e to the x power. How many remember that e to the x power can be expressed as a power series? Andrea remembers that, like this, right? That's the power series for an exponential function. And actually in section 6.1, they have a table of Maclaurin series, power series, for some very common functions like e to the x, cosine of x, sine of x, and so forth. Well, of course, this is true, but it's only true over an interval of convergence. And the interval of convergence in this case is from negative infinity to infinity. So in other words, the e to the x, that exponential function, is equal to the sum, where n equals 0 to infinity, of x to the nth power over n factorial. And that's true for all values of x. It has an infinite interval of convergence. The interval of convergence is from negative infinity to infinity. That means the radius of a convergence is infinity. And that's nice. But we have to recognize that not all power series have an interval of convergence from negative infinity to infinity. And anytime we're presented with the power series, in order to determine its interval of convergence, we have to use a special kind of test. So like for this power series here, what special test would we use to determine the interval of convergence? Do you remember it? That's right, Michael. We'd use the ratio test. We'd use the ratio test. And so what I'm going to do is I'm going to, on the next page, I'm going to show you the ratio test. And this should be review, but let's go ahead and look at it. Are there any questions so far? Okay. Well, all right. So again, just to make things a little more clean for you, a power series is sometimes a little bit. This is not actually what I'm showing here. Is not actually part of the finding the interval of convergence, but the power series is a sum of terms. It's a series, and so like for this power series, n starts at 1. So the first term you would let n equals 1, and this would be the first term of the power series. Okay, the second term we would let n equals 2. The third term we let n equals 3, and so forth. And so the first three terms of the power series look like this: negative x over 2 plus x squared minus 9/8 x cubed. We wish to know, of course, for what values of x this power series converges, and that's where we're going to use the ratio test. But I wanted just to write out the first three terms of the series just to kind of make it less abstract for you. Is this helpful, this little, is this sort of helpful just to, okay, excellent, helps you, thank you, Matthew, it helps you remember what a power series represents. Excellent, excellent. Okay, well then, if we're good with that,
Wait, can you keep
are
this
there any
for a
questions
second?
at all?
Can you keep? Yeah. Okay. Thank you.
Okay. Are there any questions at all?
I'm good. Yeah.
All right, Matthew's good. Okay. Okay, so the ratio test, the nth term of the series is negative 1 to the nth power times n squared times x to the nth power divided by 2 to the nth power. So using the ratio test, what we do is we look at the ratio of the n plus first term of the power series to the nth term of the power series, and we study how, and then we take the absolute value of that ratio, and we study how the ratio behaves. All right, and so this is the n plus first term here in the numerator. And this is the nth term in the denominator. And we're taking a fraction and dividing it by a fraction here. So what we do is we take the top fraction and multiply by the reciprocal of the bottom fraction. And that gets us here. Let me give you a moment to catch up.
I actually have a quick question about the exam. Are the remediations still going to be due the following Friday?
Oh, the way I'm going to do the remediations is I'm going to have them due on Saturday, the following Saturday.
Okay.
That way you'll have 4 days to do to tend to the remediations. Excellent question. Was that Christopher who asked that? Yeah, good question, Christopher.
Okay, so it'll be due Saturday at midnight.
Well, yeah, the remediations, to finish them, like on the WebAssign, would be Saturday at 4:55. The following Saturday at 4:55 p.m. But right, the work, turn it in midnight that Saturday. That's correct.
Okay, sounds good. Thank you.
You're welcome. You're welcome, Andrea. You're welcome. You're welcome, Christopher. Okay, so then what we do, we have to simplify this expression inside the absolute values. I don't take the limit yet. I'm going to simplify first. So I put like terms over each other. Okay. And then I simplify. When we divide, we subtract the exponents, and that's going to get me here.
Wait, did you just put the n the n and the n+1 as the same term and then just squared the whole thing?
That's right. For like this part here, so n+1 squared over n squared, that's the same as, well, that's the same as this. Think of it this way. Could you go from here to here? Would the quantity n+1 over n squared equal n+1 squared over n squared?
Yeah, I guess. I don't know. Maybe I'm just like, I don't know.
Well, it does.
I'm just having some doubts. I don't know. Yeah.
That's okay. It's good to, let me make an analogy here. Okay, so like take 6 over, take 6 squared over 2 squared. Okay, let me maybe put this in blue, get used to my stylus here. 6 squared over 2 squared is 36 over 4, which is 9. Well, 6 over 2 squared, 6 squared over 2 squared is the same as 6 over 2 squared, which is 3 squared, which is 9. Does that little example help you feel a little more comfortable?
Yeah.
Okay. Well, then this should be okay. But think about it. Think about it. All right. Well, then now we still have to take the limit.
I have a
And
question.
yeah, question, Antonio. Yep.
So for the term where you get 1 over 2 to the 1, how did you, is that just because the n in the top term is like turns to 0, or?
For that, what we do here, this here
Mhm.
is 2 to the nth power minus the n plus first power. We subtract the exponents when the base is the same.
Oh, okay. And then it's just 1/2.
And that, well, that gets me 2 to the negative first power. And that's 1 over 2 to the positive first power.
I gotcha. I was just confused because you put the 2 to the first power on the bottom, and I didn't know why the top one was. But I guess that would just be 2 to the 0 power.
Well, when you take n minus the quantity n minus the quantity n plus 1, that gets you, the n's cancel, and you get a negative 1.
Mm-hmm.
And 2 to the negative 1 is like 1 over 2 to the positive 1.
Right.
Negative exponent becomes positive exponent by.
That makes sense.
All right, very good, very good. Well, all right, let's continue on. Good question. So now, then, the absolute value of a negative is a positive, so that negative 1 went away. And the n plus 1, the quantity n plus 1 over n squared, that's always positive, so I can bring that out in front of the absolute value. And I'm going to end up, well, this n plus 1 over n, that's just 1 plus 1 over n. We're squaring that, but as n goes to infinity, the 1 over n term, that goes to 0, right? This goes to 0. That goes to 0 as n goes to infinity. And so we get 1 squared times the absolute value of x over 2, which is the absolute value of x over 2.
Is this page the end going to be the end of the example or no? I just want to know.
No, there's more. Okay. There's more. So by the ratio test, well, what we're this power series will converge when our ratio, the absolute value of our ratio, is less than 1. Essentially, what we're saying is that our power series behaves like a geometric series. Our power series actually behaves like a geometric series as we go out further and further in the series, as n gets large. Because in a geometric series, the property of a geometric series is that the ratio of a term with its previous term is constant. Well, we're getting that result too. The ratio of the n plus first term to the nth term is going to equal the absolute value of x over 2. That's a constant, right? That doesn't depend on n. And so geometric series, as you recall, converge when the common ratio is less than 1. And so by the ratio test, we're going to determine an interval of convergence by determining for what values of x the absolute value of x over 2 is less than 1. That's how we're going to determine, in part, how we determine our interval of convergence. We still have to look at the endpoints, but yeah, question.
Why did we get rid of the limit again?
Well, because it has to do with the ratio test. The ratio test, you take the limit as n goes to infinity. And
oh, sorry,
then,
you did the limit there. I'm sorry.
That's right. Here, the 1 plus 1 over n quantity squared goes to 1 squared as n gets large. All right. Good questions. Let me know when we're ready to move to the next page.
I don't understand that x over 2 is less than 1. What does that mean again?
That has to do with, okay, Paige, no problem. That has to do with the ratio test, Antonio. If you look at your ratio test, like in, if you like, do you remember in Calculus 2 doing the ratio test?
I don't think I ever did that.
Let me see. Hold on. Let me. All right, hang on. Let me bring up the ebook. One moment. One moment. Let me bring it up here. Okay, I'm looking before example 1 in section 6.1. Let me just. No. Okay. Highlight it here. One moment. Okay, let me bring it up in the ebook before we continue. Everybody's good though so far? All right, we'll come back to this. We'll come back to this. We're not done with the solution yet. Okay, very good, Christopher. Okay, so this is the ratio test that I highlighted in yellow. If you double click on your screen, you can make it a little bigger. Okay. So that's what we did. And okay, that's what we did. And we get this ratio L. And okay, so Antonio, I would have hoped you would have seen that.
Yeah, I've never seen that.
Oh my goodness! Did you, and you took calculus here at Montgomery College?
No, I took it out of my undergrad.
Okay,
Yeah,
okay,
I went somewhere else.
all right. I might have to have a chat with them. You know. All
I
right.
know my personal experience. I took it in high school, and this was the same year that COVID kind of started, and it was taught at the end of the year, and it kind of got cut off, so we didn't really talk
Oh
about
my
it.
goodness. All right. Well, I guess I didn't think about that. Yeah, I guess. Well, at any rate, Justin, you know, and now you kind of you remember it, but now you're seeing it again, which is good. Which is good. All right. No problem. No problem. So,
Oh,
okay.
I guess I have a question then. So, how can L be less than 1 if it's got a variable in it?
Well, see, what you do is you look at this ratio that you get, and hold on here.
So it's 1/2 x.
Yeah, you purposely set the ratio less than 1. And based on that, see, when you set the ratio less than 1, well, if the absolute value of x minus 2 is less than 1, then x over 2 is between negative 1 and 1. And so x is between negative 2 and 2. And so these are the values of x for which the power series would converge. In other words, the power series, if you put in values of x in the power series between negative 2 and 2 and add up all those infinite number of terms, you would get a number. You would get a finite number. So the power series converges when x is between negative 2 and 2.
Where does the value 1 come from?
I'm sorry. Well, it has to do with a geometric series. A geometric series. A geometric series has a ratio, common ratio, and if the common ratio is less than 1, the geometric series converges. If the common ratio for the geometric series is greater than 1, the geometric series diverges. So we're saying that our power series behaves like a geometric series if you go far enough out into the series. You know, as n gets large, as you go further out in the series, our geometric series, our power series acts like a geometric power series. But that geometric power series would only converge for values of x, for when the common ratio, which is absolute value of x over 2, is less than 1.
So it only acts like a geometric series if x is between those values?
It only acts like a convergent geometric series if x is between these values. That's right. But the thing is, we're not done yet, because the thing is, you see, if the common ratio, which is in this case absolute value of x over 2, if it equals 1, then the ratio test gives no information. The ratio test gives no information. And so what you have to do is when x equals negative 2 or x equals positive 2, the power series may converge for one of those values or both those values. And so what we have to do is we have to plug in those values into the power series and manually check if the power series converges at x equals negative 2 or x equals 2.
Yes, so we were trying to find the convergence interval, which
That's
is
right.
why we said, okay, we just ignore the x and say 1/2, and then that's that ratio.
But the interval, the thing is, the interval could include one or both of the endpoints. Okay, and so now what we're going to do is we're going to go ahead and plug them in. But let me give you a moment to catch up. Let me know if you have any questions.
I guess I am still confused why we necessarily decided to assume that x over 2, absolute value of x over 2 was greater than 1.
You mean less than 1?
Or less than 1, yeah, sorry.
Well, it has to do with the fact that a geometric series converges if its common ratio is less than 1. That's the reason why. And our power series behaves like a geometric power series. As you go further out into the series, the terms of the series behave like a geometric power series. But the common ratio is a function of that. The common ratio has to be less than 1 for there to be convergence. And that's right. Michael says if the power series is greater than 1, if the common ratios, hold on, let me get that back. If the common ratio is greater than 1, then it's a divergence geometric series. So you might have to review a little bit, but this is something that, it's something that, and I'm saying it might have been a while since you've seen it.
Yeah, sorry, I forgot. It was right back in the definition. I don't know. I guess
That's
I'm just
okay,
off
no
today.
problem. All right.
So are all
Okay.
of the power series going to act like geometric series in this section?
For when they ask for interval of convergence, yes, they
Okay.
should up to for n large enough. Yes. Okay, so now what we do?
Wait, I'm sorry. Could you go back for just a quick second?
Sure. Paige, you had a question. Why did it go from 1 to 2?
We had x over 2 inside the inequality. That's why it went.
Right.
So we just multiply the 2 out, and then. Yeah.
Correct. This part here.
I'm good now, but I don't know about
So good. Paige, are you okay? Matthew's good. That's right, Paige. But what's going to happen is, yeah, you would use the entire thing. That's right, Paige. But you won't. I don't know if you'll see that what you're chatting there. But yes, that's right. That's right. Okay, so now, all right, very good. So now we're going to test the endpoints, x equals -2 and x equals 2. We're going to test those endpoints. And so what I have to do is when x equals -2, I plug -2 back into the power series. That for x, I let x equals -2. And then I actually find the series. Okay, so I do a little bit of simplification, and the series is going to be equal to the sum where n equals 1 to infinity of n squared. Let me give you a moment to catch up here. Okay, so when we put x equals -2 into the power series, we get the series sum n equals 1 to infinity of n squared. Well, that series diverges. The terms, you get 1 squared plus 2 squared plus 3 squared plus 4 squared. By what's called the test for divergence, the series just diverges. It doesn't approach for a series to converge. When you add up all the terms, the infinite number of terms of the series, you have to get a finite number. Well, there's no way that this sum is finite. Similarly, if we put in x equals 2 in the power series, okay, we'll get a series, an alternating series. Okay, we'll get this alternating series. And that also diverges. That does not settle down to a number. Go ahead, Michael. Yes, yes. Go ahead. All right. Are there any questions up to this point here? Well, the last thing I need to mention is this. The interval of convergence for the power series is the open interval from -2 to 2. And the radius of convergence, you're welcome, Michael. The radius of a convergence, I mean, here I've drawn the interval. And the radius of convergence is half the length. The length of the interval is from -2 to 2, it's 4. Half the length is 2. Okay, I'll let you copy that down. Yeah, Andrea had a question about the midterm grades. So the midterm grades class, I had to get them in yesterday. That was the deadline. And so I wasn't able to include your MATLAB assignments as part of your midterm grade. I'm sorry about that. It's just the way that the date fell, But of course, I'm going to update your current course grades with your MATLAB grades. So I hope to have MATLAB grades done by Thursday. Okay, hope to have those done by Thursday. Okay, because I know you're curious how you did and all that. All right, you're welcome, Andrea. Antonio, so for the midterm grades class, I at the end of the semester, and I'm going to add 2% to your course grade. That's at the end of the semester, after your final exam is in and all the grades are in. I add 2% to your course grade, and that's to account for those occasions where maybe you couldn't finish an assignment on time and had a penalty due to the late extension. The 2% is to account for those rare occasions, but I don't add that 2% in until the end of the semester. No problem, no problem. Okay, now what I'd like to do, I'd like to show, I want to do, let me just see here. I want to show you another problem, but, well, no. Let me go, we'll try to fit that in at if we can here at the end, but let me go to something else, another skill that you need to know for section 6.1. But are there any questions so far? Maybe I can do this, but this next example class, I'm not going to be able to give you time to copy it down. Okay, this next example, I want to do another problem where we find an interval of convergence. So if you adjust this next example, it'll be on the recording. but don't take the time to copy it in your notes. Just follow along because I got to get to a third example. Okay, so here's another problem where we want to find the radius of convergence and interval of convergence for a power series. Okay, and this is the power series. The series goes from n equals 0 to infinity of -1 to the nth power times x minus 3 to the nth power over 2n plus 1. So, of course, what are we going to do? We're going to use the ratio test just like we did in the previous example. And so, okay, in the ratio test, the nth term is here. And I'm going to take the ratio of the n plus first term to the nth term, okay, which I show here. And we have a fraction divided by a fraction. So I take the top fraction and multiply by the first fraction. Yeah, sure, Andre. So don't take the time to copy it though. Okay, I'm not, just follow along, but any questions? Well, Andre, the notes, you'll have to do it from the recording. Okay, you'll have to go back and get the recording. The reason I'm doing it is I think it's helpful for you to have it. It's just I don't have time for you to have notes on it, and I'm sorry about that. It's just I wanted to. The first example, there were a lot of excellent questions. I wanted to take the time to answer them, but then so no problem. So just from the recording, you can take notes from the recording. So okay, here's the nth term. I'm going to do the ratio test, which is the n plus first term to the nth term. Here we go. And then I have a fraction divided by a fraction. I have this fraction divided by this fraction. So I take the top fraction and multiply that by the reciprocal of the bottom fraction. And same kind of thing. I reduce the expression here inside by grouping together like terms, and I'm going to have the limit as n goes to infinity of 2n plus 1 over 2n plus 3 times the absolute value of x minus 3. And this here, as n goes to infinity, the 2n plus 1 over 2n plus 3, well, that goes to 1. That goes to 1 as n goes to infinity, because the 1 and the 3 aren't going to matter as n gets large. Basically, as n gets large, you're going to have a ratio of approximately 2n over 2n, which is 1. So the absolute value is x minus 3. No, I'm sorry, the ratio, the L in the ratio test is the absolute value of x minus 3. Okay, are there any questions before I move to the next page? Okay, all right. Well, what we have to do is we have to take that ratio L and set it less than 1 to find our interval of convergence, to help us find the interval of convergence. So just like the first example, we took that common ratio L and set it and said, okay, set L less than 1. We're doing the same thing here. Well, if the absolute value of x minus 3 is less than 1, that means x minus 3 is greater than -1 and less than 1. We add 3 everywhere, and so x is between 2 and 4. And so this means our series is going to converge when x is between 2 and 4. But we have to ask the question, are there any more x values where our power series converges? Namely speaking, could the power series converge at the endpoints 2 or 4? Okay, well, at 2 or 4, the ratio test gives no information because the absolute value of x minus 3 when x is equal to 2 or x is equal to 4 would equal 1. And when the ratio equals 1, we get no information. So that means what we have to do is we have to substitute in x equals 2 and x equals 4 into the power series and see if we have convergence or divergence. And so what we do is we manually check if our power series converges at x equals 2 or x equals 4. When I substitute x equals 2 in the power series there, I put x equals 2 in right there. All right, I then, do some math to reduce the power series. And the power series becomes the series n equals 0 to infinity of 1 over 2n plus 1. Well, there's a test called the limit comparison test where you take the term. We want to determine if this series converges or diverges. So what's going to happen? Well, we take 1 over 2n plus 1, and I'm going to divide it by 1 over n. Now, I chose 1 over n. So an is 1 over 2n. Now we're done. This is now separate from the ratio test. an is 1 over 2n plus 1. bn is 1 over n. And we're going to look at the ratio of an over bn, and we get this to be a half. So because the series 1 over n diverges, it's a harmonic series. How many remember harmonic series diverges from calculus 2? A harmonic series diverges. That should be something that, okay, Andrea remembers it. All right, that's a divergent series. And in fact, okay, no problem. In fact, you see, by the limit comparison test, we're saying that the terms of our power series relative to the terms of the harmonic series are in proportion as n goes to infinity. In other words, the series 1 over 2n plus 1, that infinite series, the terms of that series are proportional to the terms of the harmonic series, okay, by a factor of 1 over 2. That makes sense. You have 2 over n, 2n in the denominator here, and 1 n in the denominator here for the harmonic series. So the fact is that the terms of our series are in proportion as n gets large to the terms of the harmonic series. So whatever the harmonic series does, our series has to do. So if the harmonic series diverges, then our series diverges. And that's by the limit comparison test. How many remember limit comparison tests from calculus 2? It would have been one that I would hope you would have seen. All right, Christopher recalls it. Okay, so this is certainly a good review if you haven't of power series. All right, so now we got to look at the other term, x equals 4, the other value. So we put x equals 4 in the power series, and we end up with this alternating series. How many remember alternating series from calculus 2? Okay, it'll be on the recording, Max. Thank you for letting me know. So we're covering section 6.1. So this alternating series converges by the alternating series test. So basically, you have a series whose terms are plus, minus, plus, minus, plus, minus, and the terms are getting smaller and smaller because the 2n plus 1 is in the denominator. So that series is going to converge. So this means then the interval of convergence for this second example doesn't include 2, but does include 4. Okay, and the radius of convergence then is going to be half of the length of the interval, which is 4 minus 2 divided by 2, which is 1. Okay, are there any questions on that second example? Okay. All right, well now let's go to the third example. In this one, let's go ahead and take a moment. This is fine. Don't worry about that page here. Okay, so now what we want to do is we want to write a difference of power series as one power series. Let me give you a moment to copy this example down. Okay, so it's important with differential, again, why are we studying these power series? It's because you're going to learn, and incidentally, we're going to have class on Thursday. We are going to have class this Thursday. You're going to learn that a solution to a differential equation can be written as a power series, and that can be very useful. So we need to be able to manipulate the power series. And in this problem, we have two power series, and we want to write them as one power series. Well, we know that the first power series has power x to the n minus 2. The second power series has power x to the n minus 1. So intuitively, we would like them both to have the same, like if this were x to the k, okay, we'd like the second power series to have an x to the k. We'd like to have the terms be the same in terms of, x to the power. We'd like the terms to be the same. All right, and that's really the key to combining the power series. We're going to do what we need to do so that both power series, the terms in each power series, the power part, is the same. Okay, so let me show you how we would do this. Are there any questions so far before I go to the next page? Okay. All right, so in our solution, what I'm going to do is I have for the first power series an n minus 2. So what I'm going to do is for the first power series here, I'm going to let k equals n minus 2. Now for the second power series, okay, I have an x to the n plus 1 power. Okay, well, what I'm going to do is I'm going to let k equal n plus 1. So what I'm doing here is I'm going to change what's called the index of the power series. Both of these power series here have an index n. N is the index. I'm going to convert the index from an n index to a k index. Right? So let's see how we do this.
I have a quick question. Why did we choose
yeah.
the same letter K? Because I feel like if we're gonna then combine them, how can we combine them if our K values have different values?
Well, it's okay. It's all right. Because you're right. You're right. We can't, like, in this second step here, when we make this change of variable, change of index, I'll call it, we have a series where the first power series starts at k equals 0. The second power series starts at k equals 1. So we can't combine those as they are, but we will. I'll show you how we handle that. Very good question. Very good question. So, okay, well, let's see here now. Let's see. For the first power series, k is going to equal n plus 2. So if k equals n plus 2, then well, the series starts at n equals 2. So if k equals n equals 2, what would the first k value be of that series? Well, it would have to be k equals 0, because 2 minus 2 is 0. That's from 2 minus 2. And then the top value of infinity, well, what's infinity minus 2? You know, infinity minus 2 is just infinity, you know. All right, and but the terms, the terms now in the power series that were functions of n are now all going to be functions of k. So c sub n would just be c sub k plus 2, because if k equals n plus 2, then that means that k plus 2 would have to equal n. And that's how we get the k plus 2 here, for the n here. N minus 1, well, that would just be, since n is k plus 2, n minus 1 would be just k plus 1. Okay, and then for the second power series, you start off at n equals 0, but since k equals n plus 1, that power series, equivalent power series, will start off at k equals 1. And if k equals n plus 1, then k minus 1 will equal n. And so that's how we get the k minus 1 here. Are there any questions on this second step? All we've done is we've taken these two power series, and with index of n, the n is the index, and I've rewritten them as equivalent power series with a new index of k. Now we want to combine the power series. Well, you know, we can only do what's humanly possible. The first power series starts at k equals 0. The second power series starts at k equals 1. So, you know, what I'm going to do is I'm going to take my my second power series, my first power series here, I'm going to take my first power series and write it as the first term of the power series plus the rest of the power series. So the first term of the power series is k equals k. We put in k equals 0, and that's what I've done. That's what I've done here. Okay, for this term, I let k equal 0 and substitute k equals 0 everywhere the k is. And that's going to get me the term 2c2. 2 times c2. But then the rest of the power series would be k equals 1 to infinity. Is this okay what I did here? Is this all right?
So
Are there
far,
any questions on that? Yeah.
but like right at that next step, I'm gonna get a question.
Okay. Well, see now we can, since both of these power series start at k equals 1 and go to infinity, we can combine them. And that's what I did here. I combined those two power series. And it might be easier to see if you're comfortable going from this power series to that power series, which I think students probably are. Well, then you can say, oh, I'm okay going this direction. Yeah, question, Matthew?
Yeah, so like the problem is like while you say, oh, going the other way is fine, you know, the only reason we can go the other way is because we've just said that in these two situations, k equals these different things, and then we combine them. Like for example, on the left, when k equals 1, you would add 2 and n would equal 3. But on the right, when k equals 1, you add 1 and n equals 2. So it goes from 2 to infinity and 3 to infinity, which I guess technically infinity is infinity, but like...
Well, the index got changed though. See that c sub k plus 2 and c sub k minus 1? The index is essentially what you're doing is let me see here. I have an idea. So let's say that for this power series here, let's say I didn't say k equals n plus 1. Let's say that I used instead like j equals n plus 1. Okay, so if j were equal to n plus 1, we'd have the series j equals 1 to infinity of c to the j minus 1 x to the j. Hold on, let me just get my little...
I agree.
Right, let me just make it so it shows nicely. X to the j. But isn't this power series the same as this power series? I mean, the indexes are j and k, but when you substitute in like j equals 1, j equals 2, j equals 3, and so forth, and then you, for the second power series, you substitute in k equals 1, k equals 2, k equals 3, aren't all the terms going to be the same?
Yeah, so the ones in the orange, I completely agree they're the same, right?
Right.
But then the problem is, like, for me, is like you represented K with two different things, and then they're in the same problem. So how would one be able to distinguish between the two Ks?
Well, think of it like this. Think of it like this. Let's say the second power series, I didn't use K. Let's say I use this J here. Okay, you're good with this. You're good with that power series, right?
Yeah, one equals the other. That's fine, but it's just
So isn't this power series here the same as this power series? Aren't they the same power series? Just with a different variable K?
yes, that's true.
So it's okay. It's okay then.
But
What
the
we did.
problem is, you then go on to have these different Ks. Like if we look at later steps, for example, you factor out an x to the K. How can you do that if K had different values?
Well, all you're doing is you're rewriting the power series. Thank you, Andrea. And let me just say, so hold on, I'm going to get back to that question. Class, so we're good here on the last thing. Matthew, I want to follow up with that excellent question. I'm going to keep it in the recording. I'm glad we actually discussed what we discussed there. But is everybody good here with the final answer? Are there any questions on the final answer?
Yeah, thank you.
Professor. Professor.
Yeah.
On that final answer, we have our power series in terms of K. But does it really matter what we call the counter? We could still call it N, right?
Right. You could go back and let N equals 1 to infinity, or J equals 1 to infinity. The counter does not matter. That's correct.
Yeah. But so will WebAssign accept N?
But I wouldn't use
just
N.
K?
I'll just say I wouldn't psychologically use N. But right, the counter doesn't matter. WebAssign is going to be very helpful in terms of telling you what counter to use. As a matter of fact, I think WebAssign is actually going to have this part written in for you already.
Okay. Okay.
Just be careful. Like in my answer, I use these braces, but WebAssign will not take those. Like for grouping symbols, it wants open. Thank you, everybody. I'm going to hang out a little bit and answer a few more questions, but thank you for a nice class. And I'll the recording of this will be here. Thank you, Christopher. Hang out, Matthew and Michael.
Yeah,
hang out.
So let me know when you're ready.
Okay. Thank you, Christopher.
Dr. Duty.
Yeah, Max.
I'm so sorry for being late. We had a really bad emergency and I was completely distracted, so I'm sorry about that.
Thank you for letting me know, Max. This is all going to be in the recording. As a matter of fact, let me go ahead and stop the recording now.
I'll